Hey everyone, and welcome to this deep dive into the world of TCP, the Transmission Control Protocol. Today, Amir, a brilliant student of mine, will be our guide. Please get ready to unlock the secrets of reliable data transfer on the internet. Okay, Amir, go ahead. We are waiting for your presentation. Thank you.
Thank you, Mr. Omid, and good evening. In the previous lessons, we named some protocols like Domain Name System or DNS and Internet Protocol or IP and talked about them. For example, we learned about the different types of DNS servers and how DNS translates domain names to IP addresses. Also, I talk about how to assign an IP address to a device and type of IP addresses, including IP version 4 and IP version 6. But before talking about another protocol, first we need to know that the primary purpose of each computer network, such as the internet, is to enable devices to communicate with each other. And this communication is not just a physical connection that is established by cables and antennas. Just as humans must use common language to understand each other's conversations, computers must also use common language to communicate with each other, which are called protocols. Today, there are many protocols such as IP, DNS, or something else. But the topic of today's lessons is a transfer protocol called TCP. But TCP is not the only transfer protocol. There is another protocol we call UDP, and we are going to talk about it after TCP. Since TCP and UDP use ports to be able to connect two computers that want to exchange data and information with each other, we are going to talk about port numbers after TCP and UDP. But before starting the main lesson, let me explain my above words with a real world example to prepare your mind for the fundamental lesson. Suppose you want to write a letter to your friend who lives in another city and a 20-floor apartment. You write on the envelope the address of the sender and receiver and the postal code of the sender and receiver and give it to the post office. In this example, the recipient and sender addresses play the role of the IP address, which I talked about in the previous lessons. And the post office, which is responsible for delivering the letter to the recipient, plays the role of the protocol. But when the letter arrives at the destination address, for the postman to find out which floor or which door he should deliver the letter to, he looks at the mailbox number written on the envelope. In this example, the mailbox number plays the role of port number, which tells the postman which floor the letter is for. I will explain the function in a port numbers lesson. Note that a person who wants to learn cybersecurity must have a deep understanding of network protocols, especially TCP and UDP, which are very important protocols. And since both of them use port numbers, after learning them, I go to talk about port numbers. Since TCP is more complicated than UDP, I will explain TCP first because if we understand TCP well, it will be easier for us to learn UDP. Okay, but what is TCP and what does TCP stand for? TCP is one of the main protocols of the Internet, which stands for Transmission Control Protocol, and it ensures that our packets, or in general our data, reach their destination correctly when they are sent. In the OSI model, which is a seven-layer model for studying and better understanding the functions of networking system, TCP is one of the protocols of the fourth layer of the OSI model, which is called the transport layer. As a result, when the data reaches the transport layer from the upper layers, it's determined whether to use the TCP or UDP for transmission to the destination computer. As I explained in the example above, IP specifies the addresses of the destination computer on the network. But to make sure that our packets reach their destination, we need to use TCP because TCP has features and mechanisms for sending packets that ensure that the packets reach their destination exactly as they were sent. To take a deeper look at the features of TCP, we need to take a closer look at its header. TCP header consists of several different parts, each one for a specific task. I will explain all of them below. TCP header length varies from 20 bytes with no bits of option field being used and 60 bytes with all bits of option field being used. And I will explain the reason for this difference in the continuation of the lesson. At the beginning of this lesson, I said that when two computers want to communicate with each other to exchange data, they use port numbers to tell each other which data goes where. The port in question here is not a physical component, but a virtual endpoint between two computers. The source port and destination port are specified in the TCP header, which I explain later. For now, we just should know that the port number is a 16-bit number. Hence, we can have a total of 65,535 ports because 2 to the power of 16 is 65,535. One of the important and famous features of TCP is called connection oriented. But what does it mean and how does it work? Before TCP starts sending packets to the destination, it makes sure that the sender and receiver are connected and can send packets to each other for its sends. If you want to tell your friend about a new movie or game, you can make a phone call. You dial your friend's number, and if she gets the call and confirms that you are on the other end of the line, she picks up. Then you can begin to tell her about the game. TCP does this by a protocol called a three-way handshake. How does a three-way handshake work? At first, the source computer sends a packet to the destination, which is called a SIM packet, and says, "Hello server, I want to communicate with you on your port 80, for example. Can you hear me?" Then after receiving it, the server responds to it, which is called a SYN-ACK packet, and says, "Yes, I can hear you on my port 80, but can you also hear me on the port you are trying to communicate with me through? For example, port 54,433. In the third step, the computer sends a packet called ACK packet and says, "Yes, I can hear you too." And in this way, a connection is established between port 54,433 at the source and port 80 at the destination. But after making sure that connection between two computers is established, how does TCP guarantee that if we use it, all the packets will reach the destination correctly and they arrive in the same order as we sent? For example, if our message was, "Hello, how are you? What's up?" It will not reach the destination as, "How are you? What's up? Hello." It's just example. In the TCP header, there are two parts named acknowledgement number and sequence number, and with the help of these two, we can make sure that the packets have reached their destination in order. The sequence number is a counter used to keep track of every byte sent outward by the sender's computer. This makes the recipient realize how many packets he has received so far and whether the packets are coming in order or not. If the received packet was according to the order, the receiver responded to it, which is called acknowledge. Acknowledge tells the sender that the packet has arrived correctly. Acknowledgement number specifies the sequence number of the next packet and the next byte the receiver is expecting on this connection. True Handshake also use the same acknowledgement to ensure that two computers are connected. In this example, at first the client chooses a random sequence number, for example, 1001. Note that in the real world, the sequence number is not small. And for example, 200 bytes of data are sent by packet. After receiving the packet, the server checks and sees that it has received a 200 bytes message with sequence number 1001 from the client it communicated with. So he sent an ACK packet to the client and says that in the next packet you should start from sequence number 1201, and I'm waiting to receive a packet with sequence number 1201, and it goes on the same way. If the ACK packet doesn't reach the client for any reason, after 500 milliseconds, the client thinks that the packet didn't reach the server and sends it again. It sends the packet until it receives its ACK. This feature of TCP, which must be sure that the packet has reached its destination and retransmit it if it hasn't, is called reliable. This TCP feature, which specifies in the sequence number section how many bytes the client has sent so far and from which byte the next packet is sent should start, is called order. Another part that can be seen in the TCP header is the checksum to provide basic protection against transmission errors. TCP uses checksums in its header. The checksum is calculated by taking the binary value of all the fields in the TCP header and the data, treating them as a large integer, and then performing a bitwise complement on that integer. The checksum is calculated by the sender using a specific algorithm. It is then stored in the header and sent as part of the data stream. The receiving side calculates the checksum on the data that is received using the same algorithm as the sender and compares its value to the checksum passed in the header. But if the value don't match the packet, it is rejected. As a result, the acknowledged packet isn't sent, so the sender should send the packet again. Another feature of TCP is flow control. TCP flow control was created to control the data rate between two computers. Flow control will help TCP to ensure that a sender isn't overwhelming a receiver by sending packets faster than it can consume. If a device receives more data than it can process or store in memory at any given time, the data is lost and needs to be retransmitted. The flow control mechanisms tell the sender the maximum speed at which the data can be sent to the receiver device. The sender adjusts the speed as per the receiver's capacity to reduce the frame loss from the receiver side. I said that whenever a packet is sent, a confirmation under the title acknowledgement is sent in response. But in reality, if an ACK was received for each packet that was sent, the network would be extremely crowded and congested. So in reality, an ACK would be received for each group of packets that were sent. When two devices communicate with each other by TCP using the three handshake protocol, the capacity of each device is determined from the beginning in the window size section of the TCP header. It means that when the sender sends a SYM packet to the receiver, further that it says to the receiver, "Hello, I want to connect with you." It says, "Hello, receiver, this is my window size, for example, 3000 bytes." The receiver also, in the SYN-ACK packet, responds and says, "This is my window size too, for example, 2000 bytes." Pay attention, don't send packets in one time more than it. TCP stores the data it needs to send in the send buffer, and the data is received in the receive buffer. When the application is ready, it will then read data from the receive buffer. Note that the buffer at the TCP layer will store the data to fixed limit and then bundle them into segments. Data is retrieved from the receiver buffer after the application is ready. Flow control is all about making sure we don't send more packets when the receive buffer is already full, as the receiver wouldn't be able to handle them and would need to drop these packets. To control the amount of data that TCP can send, the receiver will advertise its receive window. That's the spare room in the receive buffer. Every time TCP receives a packet, it needs to send an ACK message to the sender, acknowledging it received that packet correctly. And with this ACK message, it sends the value of the current receive window, so the sender knows if it can keep sending data. Sliding window in flow control. One of the popular flow control mechanisms in TCP is the sliding window protocol. In this method, when we establish a connection between the sender and the receiver sends the receiver window to the sender. The receiver window is the size that is currently available in the receiver's buffer. Now, from the available receive window, TCP calculates how much data can be sent further without acknowledgement. TCP uses a sliding window protocol to control the number of bytes in flight it can have. In other words, the number of bytes that were sent but not yet active. Let's say we want to send a 300,000 bytes file from node A to node B. TCP could break this file down into 200 segments, 1,500 bytes each. Now let's say that when the connection between node A and B is established, node B advertises a receive window of 60,000 bytes because it wants to help us with our math here. Seeing that TCP knows it can send the first 40 packets before it receives an acknowledgement. If it gets an ACK message for the first 20 packets, meaning we now have only 2 packets in flight, and the receive window presents in this ACK message is still 60,000. It can send the next 20 packets, bringing the number of packets in flight back to 40. That's the limit defined by the receive window. In other words, at any given point in time, it can have 40 packets in flight that were sent but not yet active. The persist timer. If the buffer is full, the receiver tells the sender in its ACK to not send packets at the moment so that I can empty the buffer by processing the packets in the buffer. Now, when the receiver processes the data and makes a free space in the buffer, it waits for a packet from the receiver to respond to it with an ACK message and says, "Okay, now my buffer is free, send your packets again." On the other side, the sender has stopped sending packets because the receiver told it in the last ACK that my buffer was full and not to send me the packet. In other words, after the receiver advertises a zero window, if it doesn't send any other ACK message to the sender or if the ACK is lost, it will never know when it can start sending data again. We will have a deadlock situation where the receive is waiting for more data and the sender is waiting for a message saying it can start sending data again. To solve this problem, when TCP receives a zero window message, it starts the persist timer, which will periodically send a small packet to the receiver, usually called window probe. So it has a chance to advertise a non-zero window size. When there is some spare space in the receiver's buffer again, it can advertise a non-zero window size and the transmission can continue. Finally, when the two devices didn't have more data to exchange, the sender sends a message to the receiver called FIN packet and says, I want to terminate this connection. Are you ready? The server responds with a FIN ACK packet and says, yes, I'm ready to disconnect. The client says goodbye to the server with an ACK packet and ends the connection. But let me ask a question. In computers, how is it determined whether the packet being sent or received is a SYN packet or ACK packet or a FIN packet? This is specified by flags that works as a control bits and gives us important information about the status of network connections. In the TCP header, 6 bits are next to each other in a special order and each bit represents a flag. And if its value is 1, that flag is on. And if its value is 0, that flag is off. The flags are in this order. As you can see, urgent, acknowledgement, push, reset, synchronization, and finish. URG or urgent. If this flag is set to 1, it means that this packet has priority over other packets and should be processed earlier than others. When this flag is set to 1, the urgent pointer in the TCP header is checked to see exactly which bytes should be processed first. An example of an urgent pointer is when you have written a message in a chat application and you want to delete it immediately. The packet that wants to delete the message has priority over other packets and must be processed earlier than the others. Acknowledgement. If this flag was set to 1, it means that this packet is an acknowledgement and sent to confirm receipt of another packet. Push. If this flag was set to 1, it means that this packet doesn't need to be buffered and is immediately sent to the application layer. As we understand in the flow control section buffer, is a region of memory used to temporarily hold data while it's being moved from one place to another. A buffer is used when moving data between processes within a computer. Reset. As I said above, when two computers have no data to exchange, they end the connection by sending FIN, FINAC, and ACK packets. But if a packet with the RST flag on is sent from any of the devices, the connection is immediately and unilaterally closed. TCP uses this flag in some special situations, for example, when the receiver gets a packet for a closed port. The sender or the receiver loses the state of an existing connection due to the restart or a network interruption and sends an RST when it receives a packet that doesn't match its expected sequence number or acknowledgement number. SYN. If this flag was set to 1, the receiver will know that this is a synchronization packet and it's for establish a connection. FIN. If this flag is 1, it means that this packet is a final packet to end the connection, but slowly and with the consent of both devices. Now I want to talk about the options field in the TCP header. When TCP was developed initially, the internet, memory, and technology were not so advanced and cheap. The basic headers were enough at that time for successful communication between two computer nodes. But as the internet became popular, the old TCP started to become outdated and changes in headers were required to accommodate the available change in the internet and memory. But once the TCP is so popular globally, it would be practically impossible to introduce new changes to it and deploy it on every device. So then, how do TCP and the internet come out with this solution? They left the option field just below the main headers in the packet. At the time, the use of the options field was very limited, but now every new change or optimization is implemented using the options field. This field is optional because it's used on very special occasions and isn't used in every packet. Many optimizations use the options field in the same packets and others use it when the network is congested. Here we see some of the most important items in the options field and talk about how they work. Maximum segment size, or MSS. The client talks about the packet size which it can accept from the server. This option field is used in the SYM packet when the client establishes a connection with the server. If a data packet is compared to a transport truck, with the header being the truck itself and the payload being the trailer and cargo, then MSS is like a scale that measures only the trailer. If the trailer weighs too much, then the truck is not allowed to continue to its destination. In this example, if we consider the length of the header as 20 bytes, the MSS will be 180 bytes, which means that only 180 bytes should be sent in each packet. Selective ACK. Selective acknowledgement, or SAC, is a strategy that corrects this behavior in the face of multiple dropped segments. With selective acknowledgement, the data receiver can inform the sender about all segments that have arrived successfully. So the sender needs to retransmit only the segments that have been lost. In the current scenario, the ACK mechanism is not responsive because, for example, if the loss of packets number 2 is determined according to the ACK and it's sent again, packet number 3, which was once successfully received by the receiver, will also be sent and it takes time. But in such a situation, the receiver, or in this scenario, the server, by sending a packet and using the SAC mechanism, tells the sender or the client that the server hasn't received packets 2, number 4, and 5, and the client just resends them. Timestamp. In the example we gave about ACK, I said that if the client doesn't receive the ACK packet after 500 milliseconds, it will send it again. But this time is not fixed and it's dynamic. Timestamp is responsible for setting this time. Padding. The options field is not always fixed and varies according to the conditions. The padding ensures that the TCP header ends and data beings on a 32 bits boundary. The padding always consists of only zeros. Offset. As I said at the beginning of the lesson, the length of the TCP header varies between 20 and 60 bytes. And the reason for this difference is the existence of a section called options. Regardless of the options, the length of the TCP header is 220 bytes, but the options are variable and increase the length of the TCP header depending on what is used. And the amount of this length increase is not fixed. With the help of offset, it's determined exactly how long the TCP header is and where the main data starts. Note that offset is also called header length. That's why some places read HLEN instead of offset, like in this picture. In this lesson, I talk about TCP and how it works, and we understand how TCP ensures that all packets data arrive unaltered. Moreover, it offers reliable transmission across various devices. But as I said at the beginning of the lesson, TCP is not the only transfer protocol that exists in the fourth layer of the OSI model, and sometimes packets are sent by UDP. In my next lessons, I will talk about UDP and why TCP and UDP use ports. Thank you, Mr. Omid, for your time. This was my presentation about TCP.
Okay, perfect, Amir. That was an amazing presentation. We learned so much about how TCP keeps your data following smoothly and securely. Um, I talk about our subscriber and listener. If you are curious to learn about TCP or have any questions, have a comment below. And be sure to subscribe for more tech tastic content like this. Okay, please, Amir, please mute your mic. I want to talk about foundation of reliable communication. Thank you.
Okay, also.
Okay, back your presentation and your layer OSI layer. Please open the yeah, thank you. Okay. Uh, The Transmission Control Protocol (TCP) sits at the transport layer 4. As you told Amir, if the open systems interconnection OSI model that we see in the presentation, it guarantees reliable, ordered, and error-free data delivering between applications on different hosts across networks. Unlike its counterpart UDP, User Datagram Protocol, which emphasizes speed over reliability, TCP prioritizes accuracy and completeness. But I want to talk about key features of TCP. One of the key features of TCP is connection oriented, establishes a virtual connection before data transfer. It's like and similar to making a phone call before speaking. And the next one is reliable delivery. Uses various checks and mechanisms to ensure data arrives intact and in the correct order. And the next one, an important one, is follow control. You talk about that. Regulators data follow based on the receiver's capabilities, preventing buffer overflow and packets loss. Follow control is very important in TCP. And the next one is congestion control. Congestion control is adapts data transmission rate to avoid network congestion and optimize resource usage. The next one is error detection and correction. It's important, detect and correct. Employs checksums and retransmission mechanism to identify and fix errors during transmission. But let's look inside the TCP engine. As you told, TCP engine uh, has a three-way handshake. But what is that? Establishes a connection by exchanging sync, SYN ACK and ACK packets, synchronizing initial sequence number. Another one you talked at segmenting splits data into manageable chunks called segments, each with a header containing sequence and acknowledgement numbers. Another one is sequence numbers. Uniquely identify each segment, ensuring they arrive and are reassembled in the correct order. So it's important. The next one is acknowledgement numbers or ACK numbers. Sender uses acknowledgements or ACKs received from the receiver to track delivered segments and adjust transmission accordingly. The next one is timeouts and retransmissions. If an ACK is not received with a certain time, it means timeout, the sender assumes packet loss and retransmits the segment. The next one is congestion window. Dynamically adjusts the amount of data sender can transmit without overloading the network. So it's very important. Uh, Transmit without overloading the network. Okay, let's look applications of TCP. The first one is World Wide Web, like file downloads, enable browsing, and streaming services. The next one is email. Ensure message delivery and integrity. The next one is remote access. Securely connects to the remote computers like RDP. File transfer protocols guarantees reliable file transfer, for example, FTP, SFTP. The next one, many online applications underlying communication backbone for numerous internet services. For advanced concepts, TCP options enhance connection behavior with features like window scaling and timestamps. Amir talked about window scaling and timestamps. The next one is fast retransmit and recovery. We call that RTO estimation. It can improve efficiency by faster retransmission when packet loss is suspected. The next one is selective ACKs. Selective ACKs we call SACS, SACKS, acknowledges receive segments individually, allowing faster recovery from partial packet loss. For exploring further to truly master TCP, you can venture deeper into RFC 793 Transmission Control Protocol, the official specification document describing TCP in detail. The next one, networking textbooks and online resources, explore in depth explanation and practical examples. The last one is network analysis tools. Capture and analyze TCP traffic to visualize its behavior. You can use Wireshark or similar software. Okay, by understanding the intricacies of TCP, you gain a deeper appreciation for the reliable and efficient communication that forms the foundation of the internet. Thank you for watching our video. I hope you enjoy it. For support us, please don't forget to subscribe and like, and do not hesitate for any question. Type in comment section. Have a nice time. Bye.